Hi, my name is Red and welcome to my new YouTube series where we'll be diving deep into the heart of artificial intelligence and the inner workings of neural network. So, I've designed this course so it is as beginner friendly as possible. So even if you don't have a background in machine learning, you'll still be able to understand the intricate workings of a neural network and how neural networks came to be. So without further ado, let's get started. Disclaimer, we will need to know a little bit of math, namely matrix multiplication, linear algebra, multivariable calculus, and a whole lot of imagination. Don't worry, I'll go over them briefly because I know you wouldn't do any homework before starting this course, so I'll teach you all the math components you need to know as we get through the course. What is a neural network? Well, neural network is the structure right here. This is supposed to be, for all intents and purposes, the part of your brain, specifically the neural architecture that recognizes the digits from 0 to 9. It's called the input layer. In terms of humans, that would be our eyes. So we see digits with our eyes, and these two layers right here are called brain of the whole neural network. This is where it recognizes patterns, and this is where it does all the thinking. And the last layer is called the output layer. So this is basically the mouth of the neural network. So this is the structure of the neural network we'll be working with. The first one is called the input layer, and it'll have 784 nodes in total. I took this because the dataset we're using is the MNIST Dataset, and it has images of 28 times 28 pixels. So that is total number of 784 pixels. So that's why I took the input layer has 784 nodes. The output layer is 10 because the image, the digits on the images are ranging from 0 to 9. So that's in total 10 digits. So to classify them, I've taken the output layer as 10 nodes. Middle to hidden layers, I've taken them at random. There is no reason you can take anything you want, but the input and the output, if you're working with the same data set, the input and the output needs to be same. You can take how many ever layers of hidden layers you want, and per each hidden layer you can have how many ever nodes you want as well. So I've just taken 16 at random, and I've taken 2 hidden layers to bump up the complexity a little bit, and yes, that is about it. So for now, I want you to focus on the output layer, since the network doesn't have a mouth like us, so it cannot communicate the output, right? Let's say we fed in an image of a 7, and the output can't really say it's a 7, but it has to communicate somehow. So let's see how it does that. So right here, we have 10 nodes in the output layer. Each node corresponds to a digit. And when the image of a 7 is fed into the network, the corresponding node lights up, as you can see in the figure. This is how the output is communicated to us. This is basically the mouth of the function. That was pretty intuitive, right? Okay, let's see how an image is fed into this network. So the first layer, we have 784 neurons. Why did we take that? Because the data set we have is the MNIST dataset. So the good people behind the MNIST dataset took a lot of 28 by 28 pixel images and labeled them correctly. Okay, so we're going to use those. I'm going to talk about what a pixel is. I'm going to go into depth. So this is an image of a 6, okay? So what I mean by pixels is, you see this grid, the blue boxes? So each image is made up of these small boxes, okay? And those small boxes hold a certain value. I'll get to that in a second, but let's assume there are 28 pixels horizontally like this and 28 pixels vertically like this. So the total number of pixels is 784. okay? Each pixel holds a certain value, okay? Those black pixels, we're take our input layer is taking 784. So we're taking each pixel as a node. So how does it look in our network? So we have like nodes, we have total 784 nodes, right? What about this pixel, this particular pixel? We're gonna represent, say this is the node, okay? That does not have any value in it, so it does not have white in it, so it's not gonna light up, right? But what about this one right here? This box right here, that one's totally white out, so the corresponding node would look like this, okay? So it will be all lit up. But so that makes sense, right? So whatever is white, it's gonna look like this, and whatever is like doesn't have the digit value in it, it's just gonna be like an empty node. But what about this node right here? What about this node? You see, there is some black and there is some white. And what about this node? It has more black than white. So to represent these, we're gonna do is we can say this is like 85% filled, right? And for this, we can say it's 30% filled. But to represent that, we can do is we can say all the nodes which are fully filled, like fully lit up, are 1, okay? And which are not lit up as 0. So how much would this be? What would this node look like in our network? It will look like 0.85. And similarly, this node will look like 0.3. Okay, so that's how the image is going to be fed into our input layer. Okay, so it's going to have values from 0, it might have 0.3, 0.7, 1. So the max it can have is 1, because that means the whole pixel is totally white. Okay, and that brings us to the end of the input layer. So let's look at what the first node and the first hidden layer is looking for. Let's call this the first hidden layer A1 and A2. Let this be the second hidden layer. And we can say that this node right here is looking for a pattern in the image, okay? Maybe it's looking for this edge right here, just a little small pattern. And this node is looking for a pattern here. And similarly, this one is looking for, a pattern here with a distinct shape. All right, we can say that's what the first layer is looking for. And the second layer is trying to look for bigger patterns or shapes, we can say. Maybe it's looking for a shape like a circle in the bottom side of the image. And this node right here, I should change the color up a little bit so it's easier to understand. And this node right here, maybe it's looking for like an arc, okay? And this node right here is looking for a circle in the top side of the image. Get it? So let's say if we feed in an image of 6, okay? And in the first layer, in A1, maybe this lights up, okay? That means this node lights up. And this one doesn't. And maybe this one lights up, okay? And since these nodes are connected with every other node in the next layer as well, this is going to communicate to the next layer saying, well, this piece, and maybe there was a node which got this piece and another node which had this piece and another node. They all communicated to this node right here, the second node. I'm going to use green to send out this arc. And then other nodes in the first layer sent out a signal to this node, which lit up for the... I wish this was the bottom part, but either way, I'm just going to make it bottom. And it lit up this part right here. So all we need to do is like put these two together in the output layer, to make a 6, right? So we can say that the first layer in the hidden the first layer in the hidden layers is looking for small arcs or like small patterns, and the second layer is looking for like shapes which can be inferenced from the first layers. So now to sum it up, so we know how to, in the MNIST data world, okay, we know what our network should do, you know, how it should take in the image, how it should think and look for the patterns, and how it should output the image. We know what it should do, right? We haven't put like any math to it on how it does it. We don't know that. We're gonna get to it when we get to it, but as of now, we know what the network should do to get the correct values, or to classify that particular image as a 6 if we feed in the image of a 6. Alright, so now we're gonna look at how one layer affects the neuron of the next layer. Okay, so we're gonna see from input to the first hidden layer what is happening. We're gonna take a small example and I will show you how we can write down the equations. Okay, so for example, I'm taking this example of a small network which has 3 nodes here and 1 node. So, well, let's say it has 2 nodes, but I'll do 1 node first and then I'm just gonna extend it to the second node. So it's connected like this, and it's connected like this, right? So this node is connected to every single one of these. So let's call this node as x1, x2, x3, and this node as a1, and this one as a2. So each node is connected with its own weight. So this one, and this one, and this, and this. So weight is nothing but, think of those weights as nerves connecting your eyes to your brain, or, you know, just think of them as nerves. And each one of them will have their own weight as well, okay? And this will be W1, W2, and W3. So how we can, so what we say, so here we can say that A1 is equal to sum of the dot product of the previous node and the weight. So that comes out to x1 w1 plus x2 w2 plus x3 w3. You can picture this as this being A1, and there's information coming from this node that is x1 with the connection w1. There's information coming from here as well. This is x2 w2. These two are totally independent. They have no connection to each other whatsoever, like while sending in information. So, and w3 x3. So we can take multiple of this and we can add all the terms that are feeding into the node. That is exactly what we have done here. So similarly for A2, we can say x1 w1 plus x2 w2 plus x3 w3. I want you to know that this w1, the green w1, is not equal to the blue w1. They're both different weights, okay? This is very important. So you can use different subscripts. I can, instead of, you know, I use w1 for both, but just to show you that it's coming from x1, that's why I used it, but they're not same, okay? These are some random values that we're gonna assign in the beginning, and later on we'll find out what they're supposed to be. All right, so before we move further, this is not the actual value of A. What we need to do is this, see, we have X ranging, X we've already figured out, it's a pixel, so it ranges from 0 to 1, right? 0 to 1. What about W? W can be any value, okay? W can be 350, 780, or like 800 or 2 or -3. W can be anything, okay? W can be anything. So the value of this will be huge, right? Because we're multiplying it with whatever, but it could be like 3,000 or like 3 million or whatever. The weight can be anything. So this is going to be a huge value to put in. Since we have our, remember our nodes were like in here, the X values, it's 0 or it's 0 0.1. They're between 0 and 1. So we're going to define a function for this thing. I'm going to use something called a sigmoid function to squish that huge number line of A, which is currently can go to -infinity to +infinity because the weights can be anything, right? So multiplying that weight with 0.1 or 0.2, whatever, and then adding them up will cause like it can range from anything. So what we're gonna do, this function is gonna squish that number line into 0 and 1 so that our nodes in the hidden layer have a value between 0 and 1, just like our input layer. Okay, that's what it does. A famous function to do this, a very famous function, is called a sigmoid function. So the function looks like this: 1 by 1 plus e power minus x. So, and the graph kind of looks like this, where all the values are positive, the closest, and like this. So it stagnates around 1. It hits this at 0.5, and yeah, that's it. X-axis, y-axis. So yeah, so when x is super high, like super high, then this gives a value 1. Like x is 300. If you put 300 in here, then y value will be 1. If x is like -4, -300 or -400, let's say x equals to -400, then y will be 0. So it squishes that number line between 0 and 1. That's all it does. In the first layer, we were looking for these little patterns right here. We were looking for these patterns, right? But when we find those patterns, these light up. These nodes light up, right? But what if we found a pattern, like, let's say this is the pattern we were looking for, okay? Let's say this is the pattern we were looking for. Don't worry about the border. Like, this thing is totally arbitrary. I'm just making it out so you'd understand what we're looking for. It's looking for exactly this, okay? If that node finds this in the picture, then it's gonna light up, right? But if it doesn't find it, it's not gonna light up. But what if it finds just a little bit of that? Should it light up or should it not? What if it finds a smidge, just a little smudge? Should it light up? I mean, if it lights up and it goes to the next, it conveys information to the next layer, it's gonna increase the complexity. Okay, every time a node fires, it increases the complexity of the network. So it's better to not have it fire when there's a smudge, right? Because, well, it's not really going to dictate what the outcome is going to be because it's just a smudge, right? But how much? What if the smudge is a little bigger? Should it fire now? Or should it fire when it's at least this much, right? Or should it fire when it has at least 30% of what it's looking for or 50% of what it's looking for? That's where the bias term comes in, okay? That's what the bias term is for. The bias term tells the node, every node has a bias term, and that bias term tells the node you should fire only if you meet a certain criteria. Let's say it's -10, okay? So what this bias term is telling, this part, the green part right here, should at least be bigger than 10 for the node A1 to be active. Although if it's less than the bias term, it's going to be inactive. Okay, it's like bias term is like a manager for the node. Okay, so a manager is going to look over the work that the employee has done, and then he's going to be like, well, you need to meet this certain criteria for your work to be passed along to the next department or to the higher ups. Okay, if it doesn't meet the requirement, that means the work is not going to get passed and your node will be inactive. So to sum it up, the node A1 is equal to sigma of x1w1 plus x2w2 plus x3w3 plus bias b1, and that's it. This is the equation of the first node in the first hidden layer. What about A2? We have A2 right here as well, right? It's right here, A2, see? So we have W1, W2, W3 connecting X1, X2, and X3, right? So we're going to use the same thing. Just so you know, the blue W's are different than the green W's, okay? This one should be green because it's W1, W2, W3, okay? And this one, X's are the same. X is the image, so it's fine, but weights are different. And biases are different as well. Each node has own bias, okay? So A2 has a bias B2 and A1 has a bias B1. Every node has a bias. So now that we know how the equations of A1 and A2 look like right here, right here, we're gonna represent it in a matrix form so it's easier for us to do the computation. So we're gonna go put X, okay, X1, X2, X3 in a matrix like this. X1, X2, X3. Okay, and let's call that matrix X for now. Okay, X equals to, and we're gonna put all these weights, W1, W2, W3, and W1, W2, W3. In another matrix, let's call this W equals to, and I'm gonna go ahead and get rid of all this. And what else we have? We have A. So I'm gonna write, let's take this, A equals to A1, A2. All right, so, and as well, we have bias for each node, B1, B2 as well, right? So let's have another matrix. I don't know why I write B like that, but B1, B2. All right, we have everything all in nice matrices, and according to this formula, we're gonna write these matrices as A equals to, let's see, X dot W plus B. Okay, this should make sense. Well, for now, maybe since they're in matrices, the dot product is the matrix multiplication. So we need to have them at a certain dimension to be able to multiply. So let's see if we can do that. This is at 3x1. This is at 2x3. And this is at 2x1. And this is also at 2x1. All right. So currently we cannot dot this. So this equation is wrong. But what we can do is we can put W in front and then we'll be able to do it. So we're just going to shift W to the front. So it'll become A equals to W dot X plus B. Okay, so let me just get rid of the space right here. All right, so if we expand this, are we gonna get this equation? Let's see. We should, and we probably will. Okay, so here the dimensions match. Okay, this is 2x1, right? This is 2x3 and dotted with a 3x1. The result of these two will be a 2x1, and we need to have the same dimensions to do addition in matrices. So this will add up and this will produce a 2x1. All right, let's expand it real quick and see what's going on here. So A1, A2 is the matrix, right? And W1, we'll write it as, okay, we should use blue. W1, W2, W3, W1, W2, W3. Okay, right, X right here, X1, X2, X3, plus B1, B2. All right, so when we expand this, we can write this resulting matrix of this dot product as W1 dot X1, so W1 X1 plus W2 X2, 2x2 plus W3 X3, U3 X3. Okay, that's it. Now for the second one, we can write it as W1 X1. Why did I use white again? I don't know. That should be blue. Hopefully you get the idea though, okay? Plus W2 X2 plus W3 X3. And this is a matrix of 2, 1. This is just one input in the matrix, okay? The plus, it's plus. This is like, think of it as commas. They're different at different places. That matrix, if it didn't have values, it will look like this, okay? And this matrix is just this. This is how this matrix looks, even though it has a lot of equations. And we add B terms, B1, B2. Oh, wow. Okay, so B1, B2, that have the same 2x1. So we can just add it to each element. We can just add it. I'm going to take out these brackets, and just put a plus here. So the resulting matrix is also a 2x1 matrix, which is nothing. On the left side of the equal to sign, we have A1, A2, which is nothing but that means A1 equals to the first term, which exactly represents this term right here without the sigma. So apparently we need to put a sigma right here. All right, so that is our term represented in matrices. So this network can be represented as A, this layer, we're calling it as A, these node layer. This layer, we're calling it as X, and the weights are represented as W, right? So we can write this as A equals to sigma of W dot X plus B. B, each node has a bias term. So this is the equation of a layer. This is hidden layer. Layer equation Okay, so similarly for our actual neural network, let's come right here. This is our actual network. It does not seem to have, okay, this one right here. This has the sizes, how many nodes we have. So we can do that right here. So we can put this as x, and we can give the dimensions as 784, comma 1. So this 1, we're taking it as 1 because we're feeding in one image now. Like think of the image 6. But this, while we're coding, it's going to be n. That will be like number of images fed to the system, number of samples. Okay? Samples, or you can say number of images. X is nothing, this n is number of images. Okay? So for now, we're taking it as 1. So only we're feeding in one image. So x has a dimension of 784, comma 1. And what about A? A has 16 nodes. So A's will look like 16, comma 1. A1 at least. What about A2? We're calling this A1, this A2, this X, and let's call this output O. So A2 will be 16, comma 1 as well, because it also has 16 nodes right here. And the last one has 10 nodes, so output dimensions will be 10, comma 1. All right, so that was the easy part. Let's say these weights, let's call these weights W1, these weights W2, these weights W3. I mean all of them. The matrix we're calling W1, W2, W3, okay? It's good if you give subscripts, but it's going to be fine either way, okay? So W1, what do you think the dimensions of W1 will be? Okay? Think very carefully. What would be the dimensions of W1? That is, how many weights will be in this matrix. So I'll tell you an easy way to do it is look at this node, okay? How many weights does this node have? It's connected to all the previous nodes, right? This node right here, the A11, the first node in A, is connected to all the previous layer nodes. So how many nodes are in the previous layer? So 786 connections to the first node. And again, 786 connections to the second node, and the third node, and the fourth, and the 16th node also has 784 connections. So we can write it as 784 connections x 16. I'm using comma. You can use x. These are just the dimensions. So W1 kind of looks like this. So we'll go W1, W2, W3, so on, W784. That's for the first node, the pink node, okay? Let's call this the blue node. I'm using colors to represent different, you can use subscripts, okay? We usually use subscripts, so we'll give it a variable and give W a variable as well, and we'll show, W will have two variables, which will show which node it's coming from and which node it's going to, okay? So I'm saying if this node is like X1, okay? That means that's the first node in the X, and this one, if we call, we already gave A1 to this, so we'll call this A1 and 1. That means first node, first layer's first node. We can write W as A1, 1. That means it's going from X1 to A1's 1. Okay? What about this second one? We can write, it's going from to W2. It's going W2. The 2 is the X subscript. That means it's going from the second node of X, X2, to the first node, 1. So 2, 1, W2, 1, so W2, 2. But I'm using colors to make it easier. So let's see. For the second node, it's connected to every single one, right? It's connected to all the nodes in the previous layer, and all of them are connected with weights. So W1, W2, W3, so on, W784. so on up to, this is for A11, the first node in the A layer. This is for the second node in the A layer, A1 layer, and so on. This is for the 16th node, 16th node in the first hidden layer. Let's give it 6. Well, let's give it green right here. This one is also connected to all the previous layer nodes. So this will have W1, W2, so on, W784. Okay, so that's how that W1 looks. A1, it's pretty self-explanatory, isn't it? A1, so we'll have all the nodes. So A11, we can call it A12, A13, and so on up to A116. Similarly, A2 will have A21, A22, A23, and so on till A216. These are just one entries, by the way, just one entry, 16x1, 16 rows, 1 column, 16 rows, 1 column. Okay, output will also have something like that. O1, O2, O3, so on, O16, we can write it. Okay, so let's see how A1, which is 16, 1, equals to W1 dot X plus B1. And obviously every node has a bias, so it will be same as this A1, which is nothing but 16x1. For each node there will be a bias term, so it will be B1, B2, B3, so on, B16. Okay, we need to do sigma. All right, the sigma doesn't change anything. That means if I put a sigma on a matrix, let's say A, B, C, D, I put sigma on that matrix, that means it's just going to be a matrix and each element will be sent through the sigmoid function. That's what the sigma means. Sigma of D. Okay, that's what the sigma means. All right, so let's look at the dimensions first. So we know the multiplication is correct. It's 784, 16. And X has a dimension 784, 1. And B has a dimension 16, 1. So we're going to have to turn X around. We want the resulting. This should result to 16, 1, okay? Because there's an equal to right here. So these two need to have the same dimensions, obviously. So how can we do this? What we can do is, this is a plus right here, okay? So just these two needs to be 16, 1 somehow. So I'm going to flip W. I'm going to write W1 dot transpose dot X. So that will make it 16x 784 multiplied by 784, 1. And this will get canceled and we will be left with 16, 1 for W1 transpose X term, and we're going to add B1 to it, and it's going to end up having A1. Same dimensions. So that was for dimensions. I'm going to expand this just to show you how the A1 is storing those equations. I already did it before, so it's the same thing, but I'm going to expand for 1, just for the first node. I'm just going to expand for this node exactly. So if you want to see, I'm going to expand for A1, and it's going to apply for everything. So let's see how A1 looks. So right here, this is A1, the whole matrix. I can write A11, A12, so on, A116. And W transpose. So that is 16x 784, okay? All right, like this, 16x 784. That means this has, let's write pink first, blue second, right? Okay. W1, W2, W3, so on, W784. Similarly, W1, W2, W3, so on, W784, and so on till the 16th node's weights, okay? This node was the, okay, green, right? This node's weights connected to the previous layer is right here, W1, W2, W3, so on, W784. All right, we're dotting this with X, which is 784, 1. This is how X looks. Let's put it red. X1, X2, X3, so on, X784. Plus a little B1, B2, B3, so on, B16. And whole thing is run through sigma. Okay, that's not a big deal. We'll just look over it. All right, let's expand for the first term. So this will multiply with this, W2 multiplied with X2, W3 multiplied with this, and so on and so forth. And the last term is multiplied with last term, right? And added. So we can write it as X1, X2, plus X3, plus and so on, plus X784, W1, plus W2, W3, plus and so on, plus W784. Okay, that will be the resulting matrix from this, from these two. Now we're just simply going to add the B1 term to the end of it. Okay, and similarly for the next one will be the same. Will be X1 plus X2 plus X3. I'm going to write the weights. I'm just going to change the colors. That's why I'm writing this first. And then let's go blue. W1, W2, W3, W784 plus B1 is B2. So on. It'll have 16 terms, and the last one will be with green, right? W1, X1 plus W2, X2 plus and so on plus W784, X784 plus B16, okay? This is a 16x1 matrix, and this looks the equal on the left hand side. We have A1, A2, A3. So A11, A12, A13, so on, A116. Get it? So each term, that's the equation for each node. That's how we're representing it in matrix form. So I want you to watch the video again if you didn't get it, and if you got it, good for you. Okay, pretty simple stuff actually. If you know basic matrix multiplications and basic matrix functions, you'll be able to understand it pretty fast. And yeah, so according to this, we're just gonna derive all the functions real quick. I'm just gonna write all the functions really fast, so hopefully you understand what's going on. So we've already written the function for A1. It's nothing but sigma of W1 X plus B. It could be the other way around, but I'm just writing the equation as an equation. I'm not looking for this, what do you call it, the dimensions of the matrix right now, because I'll look for it later, but I'm just writing a rough equation of how it looks like. I can like move around X and W, or I can transpose X or W to match the dimensions later. All right, that's A1. What do you think A2 equation will be? We know this will be B2 because A2 has 16 nodes and each node has a term B2, but what will be here? So we can write W2 here, right? And instead of X, we'll go with A1 because that's the previous layer to A1. So for O equals to weight W3, and the previous layer is A2 plus B3. So these are the equation for your forward pass. Forward pass. What does that mean? That means if we have these equations, right? If we implement these equations, and that means if we feed in this image of a 6, we'll get some output. It won't be the correct output, but we will get some output because we have output right here. We have an equation for the output. So this is where the x goes in, and the output, we get it from this equation. So congratulations, you've made a person. Okay, so since I related it to eyes, brain, and mouth, you have made eyes and mouth. So when these eyes see a picture of 6, the mouth says something. Well, it says something, you know, there are 10 digits and the mouth can say anything actually. It just says some random thing. It does not clearly classify it, but we've made this much progress. Now all we need to do is train this network to correctly identify these images. Okay, and we'll see that in the next video.